Hello, everyone. I'm here instead of Vladimir Ignatev. I'm his employee. I'm a chief geophysicist of Geodevice company. So my name is Roman Rimakov, and I will look on my notes as, because English is my native language. So I think you will excuse me for that. I'm a representative of Geodevice company. Today we will have a talk on a topic modeling as an essential part of seismic studies, application of full wave modeling technologies in mining. I will use an examples created with Tesserol software of Tesserol technologies in my talk. Just a few slides about our company. Geodevice is an international multi-method geophysical equipment manufacturing company with 3 offices in different parts of the world. We are producing land and marine magnetometers, suspectability meters, and electrical resistivity, electromagnetic systems, and seismic equipment as well. I want to show you just one slide on the equipment we make to make it clear why we ourselves use seismic data modeling. This slide shows different equipment for seismic, magnetic, and electric studies. Without a deep understanding of the processes, without modeling and a large number of tests, and understanding of optimal system of observations, we would not have been able to make great instruments. Okay, now let's get back to our topic. Modeling is well established for various seismic methods and is most widely used for oil and gas surveys. However, if in oil and gas seismic surveys the methods are often standard and we can always guarantee an acceptable result, in mining geophysics we have to invent a method each time for a specific problem. Without modeling, it's almost impossible to. Today I would like to review the application of modeling to mining geophysics. We will begin with the question of what modeling is in relation to seismic explorations. We will formulate the peculiarities of modeling in our geophysics, and we will consider some examples of successful application of modeling to practical examples. Modeling itself is the solving of a direct problem of geophysics, of seismic surveys in our case, and to simplify, we create a model of geological section or volume, define the properties of rocks such as velocities, densities, and specify the system of observation, which include locations of sources and receivers. Next, with the simulation of the propagation of the wave field, we get seismic geysers. Geological model can be assumed from a priori data or created from several input data such as gridded layers, well logging, or VSP borehole data. An acquisition geometry is set on the basis of possibilities, available equipment, and desired result. Then Tesserol software calculates the synthetic geysers from which final results such as stacked or migrated sections can be created. You may use these outputs to analyze and come to conclusions about the effectiveness of the seismic method to image your geological task. In most cases, the process is iterative until you will get a satisfactory result. I just want to show you how the process of modeling looks like. Here we have a geological model with a complicated geology. Properties of each layer are shown with color. Here it reflects velocities of P waves. System of observations is also set on the surface. Here how Tesserol simulate wave field. Tesserol allows to simulate the field seismic data for media of any complexity, as you can see. And here is the result. Tesserol is intended to use full wave modeling. That means the result would be as accurate as it can be. If applied correctly, the data looks like then you can obtain in field works. That allows to teach specialists to test processing techniques and create beautiful demonstration with proposed result for the customers. Having snapshots and of the wave field together with seismic geysers is also making it very clear to distinguish different waves on the seismic geyser and to understand the processes. For the task of detecting ore deposits, electromagnetic geophysical methods are most often used. However, the most accurate results regarding the structure and geometry of ore bodies can be obtained using seismic surveys. There are also geological conditions where electromagnetic methods cannot provide good results. So let's understand in which cases seismic surveys can help us. First of all, of course, in cases where sedimentary cover does not allow us to detect ore deposits by electromagnetic methods, or geological cross-section is difficult to distinguish for them, seismic surveys may be very helpful in that case. Mineralization zones also changes petrophysical properties, in particular apparent porosity, density, and compressional velocity, and as a result, causing variation in seismic impedance allow us to indirectly take seismic reflectivity as an indicator of plausible alteration intensity and zones of likely fluid interaction. And another case is rock alteration zones, which by definition outlines the change of mineralogy of a rock as a result of some variation in depositional properties, which makes these zones identifiable by seismic exploration. But to apply effectively seismic surveys in all of these cases, we need to use modeling firstly. Most cases will be unique and require a customized methodology, which is what modeling can help us with. In order to not be obstinate, I have prepared several examples of successful application of seismic survey together with preliminary modeling. Let's consider examples of different ore deposits. Here is an example from Nevada. The gold deposits here are formed by fluid sediments and are confined to natural traps, which allows us to use seismic surveying in its classical application to search for structural traps. In addition, we can determine the extent of ore deposits by altered acoustic impedance, just like in oil and gas explorations. Here we have a geological cross-section interpreted based on previous seismic surveys and borehole measurements. Synthetic geological model with thin lenses represented alteration zones. It was built in Tesserol. Seismic response resulting from contrasting impedances due to heavy alteration and subsequent decalcification was the dominant motivation behind this study. Thin lenses were placed at two individual locations with representative within the representative geological model, here on the right. To understand the possibilities of seismic method, modeling of decalcified zones of several thickness, like 5, 10, or 20 meters, was performed. So on the right, you can see thin lenses on the cross section, and on the left. And on the right, you can see the results of our modeling. And the analysis of synthetic seismograms showed that the seismic survey method of reflected waves has a significant potential for detecting gold deposits, especially confined to decalcification zones. You can see that from 5 to 20 meters, there are two bright spots on seismic geysers that reflect this. That is the reflectivity increased in proportion to the thickness of these ore bodies. As a result, samples of gold content were carried out in numerous wells, the network of which covered the main area of seismic studies of this gold deposit. Next example is on nickel deposits found in Australia. This is an example of work of Professor Professor Milovan Jurcevic, Curtin University. Here in Western Australia, we have a nickel sulfate deposits on a significant depth, up to 1 kilometer. A simplified geological model containing a nickel wedge body situated at the top of the ultramafic basalt interface and corresponding zero offset seismic response computed with tesseract. The nickel wedge is beyond the resolution limit for seismic geyser, for seismic surveys. Hence, the reflectivity is roughly proportional to the thickness of the body. From modeling we made, it is clear that very thin ore bodies, less than 3 meters thick, will not give noticeable amplitudes. The greater the thickness of the body, the greater amplitude of seismic reflection, and from some point it becomes noticeable to identify. Here we can see that from 3 meters thickness, we can distinguish the effect of nickel ore body. Another case, construct thickness, deepening nickel sulfate body located close to the ultramafic basalt interface. The same modeling parameters were used as before. The interface pattern changes from constructive to destructive. Constructive shown is with black arrow and destructive with orange ones. As a function of separation distance between the nickel body and the ultramafic basalt interface. In general, a weak moderate amplitude characteristic is expected with a small gap, but if ore body is located at sufficiently large distance from the interface, for example, a gap of 5 to 10 meters, with such large gap, the signal amplitude increases noticeably, which also make it detectable. Another example from Australia is the Macleay ore body that forms part of complex of nickel deposits. It consists of narrow, steeply deepening, shallowly south-plunging ribbon-like accumulations of massive and semi-massive with minor disseminated nickel sulfides. The mineralization here is located at contact with the basalt unit. Also, host rock have been subjected to metamorphism, structural modification, and intrusion by igneous and dike-sand siles. There were drilled 2 inclined boreholes, which were used for seismic studies. With these boreholes, we used cross-hole seismic reflection method, which provides significantly higher resolution as different type of source was used and sources and receivers were placed directly in the studied medium. On the left is the ray path diagram from one source position, and as you can see, the medium is well covered with the rays. The reflector of interest is distinguished clearly with high resolution result on the right. It's shown with orange arrow. Another example is the volcanic sulfide or barren lenses. This covers various types of ores. And in this example, massive sulfides are distributed in composite lenses, and therefore the future of mining operation depends on continual discovery of new lenses. This Rosebery volcanogenic massive sulfide deposit is a stratabound massive sulfide deposit of peritic mineralization made up of 16 individual ore lenses with up to 12-meter thickness. Here, with blue square, the area is chosen for a simplified model and cross-hole seismic reflection, again, method was modeled. The deep and depth of ultramafic basalt interface as a fault and preserved, and the migrated images counter the geology to a high degree of accuracy. But cross-hole seismic reflection provides a superior migrated image that correlates and contours of ultramafic basalt interface, and the fault structure is very well distinguished. Let's include in our model self-feed or lenses. So our model looks more like real geology we met in this place. And here is the input geological shown on the right. And the model create on the left, geological section shown on the left, and the model we created in Tesserel shown on the right, synthetic model. And here are the results of cross-hole seismic reflection imaging. After including all lenses, it looks like this. Let's overlap the result with initial model. As we can see, major ore lenses as well as host rock boundaries are imaged well. I cannot. So mostly most lenses is well distinguished on seismic result of our synthetic model. To conclude, at the moment, modeling is not widespread among seismic companies, but it's simple and intuitive modeling tools that do not require additional training are already available on the market, and moreover will allow geoscientists to raise their level and level of their investigations. And modeling is also replaceable for testing scientific hypotheses and training employees. Thus, with full-wave seismic modeling, full-wave seismic modeling may be applied in one or another way for various seismic methods used in mining industries. For instance, as proof of concept for following development stages, for testing of seismic data processing technologies and their comparative results, and for geohazard and risk mitigation. Thank you for your attention. That's all. If you have any questions, or you can ask us on our booth of Geodevice company. Thank you again.